you mind shutting the door? Thank you. All right. So I have posted the answers, most of the solutions to most of the homework problems. I'm not doing every single one of them because some of them are repetitious and it's going to take too much time. So if the concept changes, I'll do a problem. But if the concept stays the same, I'm just going to maybe show you one example or something like that. We're going to finish up 10.2 today, and then we're going to get into 10.3. I hope to finish 10.3. Once we get past 10.4, then things start to pick up. Okay, most of what we're doing right now is very, very mechanical. A lot of you have seen vectors before, so just bear with me. Trust me, if you have not seen Cal 3, it will feel like a calculus class before you know it. All right. Okay, so we were talking about vectors last class, and in this example, we're asked to find v plus u, u plus w, and then v plus u plus w. And I'm just going to work these on the board. So let's do v plus u first. And what we're supposed to do when we add two vectors is attach the tip to tail. Okay, so if I'm going to do the vector v, and I'm going to add to it the vector u, and all I'm given is a picture of u and v and w, then what I need to do is take v, leave it where it is, and add to it u. All right? That's what I could do, right? So let me do that first. I'm going to leave v right here, and then I'm going to take u, which is this vector here, right? And I'm going to move it. Vectors you can move around, right? So I'm going to move it just maintaining the length, move it over, move it down like this, and I'll get something like that. Okay, so does that look, how's that look to you? Boy, that doesn't look good. Go back. Man, the projector is shaking. I can see the whole screen vibrating up here. All right, this is u right there, right? So what is v plus u? Have I drawn it yet? No? What is it? It's a vector that goes from where to where?
From the tail.
The tail of v to the tip of u. So the vector that goes from here to here, that is v plus u. And once I have that vector established, I can move it around, right? I can move it up and over. I could orient it at the origin if I wanted to. But that is the vector v plus u. The next one is u plus w. So I'm going to leave u where it is. I'm going to take the w vector and attach the tail of w to the tip of u. So I just need to move it up, you know, and then over. So I can go up, down, left, right. I just can't turn it, right? Because then I change its direction. So what do you say? Something like, I don't know. Is that good enough for you? Good enough? All right, so this is w. And then u plus w will be the vector going from the tail of u to the tip of w. So u plus w is there. And then the last thing we want to do is just practice doing three vectors, v plus u plus w. So what could I do if I were going to do this all on the same picture? What could I do here? Just take, we already did v plus u, right? V plus u was v plus u, right? And then I could take w, translate it over, move it up, and attach it right here, couldn't I? So that's what I'll do. I'll just take w, and I'll place it right around there. So the vector v plus u plus w will start out at the tail of v, right? Go out, up, up, and that'll attach to the tip of this was w, right? So going from here to here. I don't know how the color is going to come out on the video, but it's this blue vector going from here to here. That is the vector v plus u plus w. Any questions? Pretty straightforward? Yes?
Just looking at your vector drawing, I don't know if there's like W. Just added to the tip of U and V, right? And then you do that blue line. Should it go to the 2 or not?
To the 2, what 2?
0 to your point?
No, not 0 to the point, no. If we didn't move v, okay, if we didn't move v, then we add, and then we go from here to here. Now, if I wanted to, I could move this up and over to the origin if I wanted to. But I think what you're asking is it this vector? Is that what you're asking or no?
No, I think the point, should it be exactly?
Oh, is it exactly? I don't know. I'm eyeballing this here, you know? That's, if I had a straight edge and stuff, I could get this a little better, all right? It's just practicing tip to tail stuff. That's all this is. All right. The next example, or next note, is how we add vectors mechanically. In other words, if someone gives us the vector visually, we saw how to add them in the previous example. But if someone gives you the vector and they give it to you in what's called its component form, which is the form up there like they have u, and maybe it's a two-dimensional vector like u1, u2, how do we add a vector like that to another vector? So if we're given two vectors, u is u1, u2, and v is the vector v1, v2, then to add the two vectors together, all you do is add the components. It's very straightforward when it comes to vector addition. You take the first component of u, add it to the first component of v, that's your first component of the sum. Or the sum is the first component of the new vector. And then same thing with the second components, or y components. Subtraction works just the same. If you're going to go and take u and subtract v, then you subtract the components. Now subtraction, the order matters, doesn't it? Right? So if I write u minus v, this is what's done. But if you write v minus u, these all have to switch, and that will impact your answer. If you go to three-dimensional, then you just have a third component that you add. So everything just falls the same as it does with 2D. So last class we talked about vector notation, and we use these angle brackets, right? I just want to point out that there are other notations used for vectors that you may see instead of angled brackets. You might see a vertical column instead to represent a vector. If you take linear algebra, most of the time when you represent a vector, you use a vertical column instead of angled brackets. It just depends on the textbook, the author, what class you're in. You know, there's different variants of how you represent vectors. A three-dimensional vector would be written like this. And the reason why we do that in the linear algebra class is because we find later that this is part of a matrix, and so it looks better when we put a matrix next to a column vector. So just different notations. Everyone understand? And then the I, J, K, y'all seen that in physics? I hat, J hat, we're about to talk about that. So there's another notation. Did I? Okay, so I don't have an example of that. So right now, all we've done is we've talked about if somebody gives you two vectors, we can add or subtract them, right? You can add them together or subtract them. What about multiplying? Well, when it comes to multiplication in vectors, there's actually three different types of multiplication, all right? There's three types. There's scalar multiplication. I'm just going to put this up here as a summary. Vector multiplication. I'm just going to put mult for short. We have scalar multiplication. We have a second form of multiplication, which is the next section, and it's called the dot product. And then we have a third form of multiplication when it comes to vectors, and it's called the cross product. And this is 10.3 in the book, and this is 10.4. We're in 10.2 still. So 3 different multiplications. Now this is weird, this is different, right? Because when we have numbers, right, in our number system, if I tell you to multiply 4 times 5, everybody understands what to do, right? And you just get 20. There's only one type of multiplication, and that's it. But when it comes to vectors, there's actually 3 types of multiplication. There's scalar multiplication, dot product, and cross product. So which is which? How do they differ? Well, we're starting with scalar multiplication. Scalar multiplication is taking a vector and multiplying it times a real number, a constant. So it looks something like this. C times the vector v. So you notice my notation here. I have a very small dot, and that's because in the next section I'm going to use a very heavy dot like that, and it's going to be a different type of multiplication. So if you can barely see a dot there, that means I'm talking about scalar multiplication. So C is a number. C is an element of the real number system. So C is a constant. I'm going to multiply it times a vector. An example of this would be something like 2 times the vector u, which I could say maybe 2 times the vector 3, 4. You see how this looks? A scalar times a vector. So whenever you have this sort of multiplication, the number that you multiply geometrically is doing something to the vector. All right? It's doing something to it. It changes the shape. So if the absolute value of C, so if you take the absolute value of this number out here, if the absolute value is greater than 1, what it's going to do is it's going to stretch this thing out, make it longer. If C is 2, it'll double the length. If C is 3, it'll triple the length. If the absolute value of C is between 0 and 1, it's going to shrink it. So if you put a 1/2 in front of a vector, it's going to be the same vector but half the length. All right? What's wrong? Oh, okay. All right. All right. If C is negative, what happens is that it flips the vector over. It points it in the opposite direction. So this little animation shows all of this. I have a vector v, okay? Well, I don't know which is which yet. Let me extend this out. There we go. So the red one is C times v. All right, so v is this vector. If I do 2 times v, I know it's hard to see that too, but if I do 2 times v, it's going to double the length. Everyone agree that looks like double the length? Same direction though. And if the original vector was the vector 3, 3, the new vector is doubled 6, 6. Very straightforward, right? Now I can move v around. Oops, right? And you can see that if I make v longer, then of course 2v gets longer. But let's try and take a number in front like C. Let's make it like half. So you can see the red one is half the length of the black one now. And then what if we make C negative? Goes in the other direction. So if I multiply v, the vector v, by the scalar -2, it's twice as long pointed in the opposite direction. And this will work in 2-dimensional space or 3-dimensional space. In 3-dimensional space, a little harder for me to show you, but imagine you have a vector, we call that v. Negative v would be like that, right? Got it? Okay, anything else we want to talk about here? Oh, what if I multiply a vector times 0? What do I get? The 0 vector, okay? You get the 0 vector. Remember, there's a difference between the number 0 and the 0 vector. So this is really saying I take 0, I multiply it times some vector, I'll call it v1, v2. Then the 0 kind of distributes through, doesn't it? And it creates this, which is the 0 vector, which would be a point at the origin, really. But it's the 0 vector. It's a vector that has no direction and no length. Any questions on that? Okay, so this brings us to a definition. What does it mean for two vectors to be called parallel? Well, any two vectors are said to be parallel if they are scalar multiples of one another. That's all it takes. They don't even have to be pointed in the same direction. They can be pointed in opposite directions. So if I'm going to write this, let's say I'm saying that V, have you all seen that before, parallel? Is that okay if I write two lines like that? V is parallel to U, right? Means that V equals what? How is it connected to U? It has to be a scalar multiple. So CU. Now I'm going to stop putting this dot, okay? And the way that you know that's multiplication is the same way that you used to know that 4x is multiplication, right? 4 times x? Yes? So that's what this definition means. Okay, for two vectors to be parallel, it means that V is some scalar multiple of U. Could I have written it this way? U is some scalar multiple. It may not be the same number, so I'm going to use a different letter. How about call that C1 and we'll call this C2. These mean the same thing, don't they? V is a multiple of U is the same as saying that U is a multiple of V, scalar multiple of V. Here's an example of two vectors that are parallel. 3, 2, 1, and the vector -6, -4, -2. Those two vectors are parallel, right? And the way we would figure that out is just trying to figure out if there's some number I can multiply this by to get this, which in this case would be what? -2? So what you would do is you would say, how do I turn 3 into -6? Well, I multiply by -2, right? Now, all the other things have to be the same also. If I take 2 and multiply by -2, do I get -4? Yes. If I multiply 1 by -2, do I get -2? Yes. So that would be a scalar multiple. So whatever this number is has to work for each one. It can't be like -2 works for this one, and then 3 works for that one, and then 5. Same number for all of them. All right. No questions? Was that a question? No? All right, so now we talk about the magnitude or length of a vector. So if you go back and you look at some arbitrary vector, let's say in two-dimensional space, and we want to know how long it is, does it make sense to you that we would just apply some sort of Pythagorean theorem or something to it? So if this is the vector, let's call it V, then we know that we could rewrite V in its component form, V1, V2, right? We know that the distance from here to here should be V1, and distance from here to here, right, should be the V2, the y coordinate or y component of the vector. So a squared plus b squared should be equal to not V, but this length, right? So we use the absolute value to represent that length. So V1 squared plus V2 squared should be equal to this length squared. And then you take the square root on both sides and you get this formula. Does that make sense? And then if you go to three-dimensional space, it's the same thing. So this is an important subtlety in notation. If you write this down, then you cannot say V1 squared plus V2 squared equals V squared. Why can't I say that? What, how do you mean?
It could be facing the opposite direction.
You mean V could be the other direction? I suppose, but that's not what I'm trying to get you to see here. It's something more subtle than that.
The magnitude has to be in brackets.
Yeah, why do I have to have the absolute value around this? To signify the magnitude. Why doesn't this make sense?
Possible.
Oh, then
What is V1? Is V1 a number or a vector? It's a number. You square it, you have a number, right? Plus V2 is a number. Square it, you have a number. What's V? It's a vector. V squared means V times V, right? What sort of times do you mean here? You can't say scalar because this is not a scalar, right? That's not a number times a vector. This is not scalar multiplication. So what type of multiplication is it? Dot product? Cross product? See, there's three of them. So it's neither one. So the thing is, this doesn't make sense because you can't have a number equal the product of a vector times itself if we don't even know what you mean by that, right? So that's why we have to say the length of V squared. Now, all vectors have length. So if I take this length and I square it, then this identity works. So it's just a subtlety in notation. If you draw that, that is not correct. If you're trying to set up a Pythagorean relationship, you have to put the magnitude. All right, I'd like to do an example. Well, let's see what the next example is, and then might do something different. Okay, so here's this example. Let's do example 3, part A. We have two vectors written up there. Can everyone see those clearly? Let's do part A. We want to find and sketch the vector V minus U. Let's start by drawing it, and then we'll do it mechanically, like we'll actually, since it's two-dimensional, this should be easy to draw. So let's start with the vector V. Let me draw V. I go out 2, up 3. And I'm going to call that vector V. All right? The vector U is the vector -1, -4. So -1, that's U. We good? All right. I want to take the vector V and I want to subtract U. Well, we didn't talk about how to subtract vectors visually, did we? We just talked about adding, and when you add, you did what, like tip to tail, right? So what I'm going to do instead is I want you to look at this V minus U. I want you to look at this as actually being V plus negative U. Now, what is negative U? It's U in the opposite direction. This is scalar multiplication, isn't it? This is really like -1 U. So that's U with a number in front of it. The number is -1, so it flips it in the opposite direction. Same length because it's 1. So what I could do is I could say take V and add to it this vector U pointed in the opposite direction. So why don't I draw U in the opposite direction? What would it be? What would the negative of this vector be? 1, 4? Something like that? That's the vector what? The blue there is the vector -U, right? Now take V, take the tip of V, and paste the tail of U onto it, or -U onto it. So I'm going to bring it up and over like that. Go with me? And then the result, right, the answer, V minus U, is the vector that goes from the tail of V all the way up to the tip of -U. I'll label -U here. Things are getting a little bit messy. Sorry. That's a -U right there. Negative? I should have put it. I said it. I didn't put it. Okay, that's it. That's how you do it visually. But now let's do it mechanically. So if I'm going to do this mechanically, algebraically, then all I need to do is write down the vector V, which is the vector 2, 3. I want to subtract the vector -1, -4. And from what I had on the board earlier, vector addition and subtraction is very, very clean, isn't it? You take the 2, subtract -1. So 2 minus -1. And then I take the 3 and I subtract -4. So what does that result in? The vector 3, right? 3, 7? Does that red vector look like the vector 3, 7 to you? 1, 2, 3, 1, 2, 3, 4, 5, 6. Perfect. Right on. Dead on. 7, 3, 7. Close enough, right? Get the idea here? Now, when I do these examples in class, I do not intend on working through every single example, all right? This is stuff that you could now go and you could try, on your own, go do B, C, and D. If I feel like there's maybe 2 I should look at, I'll look at 2. Let me help you just set up D, but I won't actually go through it. All right, so if I were going to do D, I would take my vector, here was that vector V, and instead of doing V minus 2u, I'm going to go plus -2u. So you remember where u was, right? U was down here like this. So negative is going to do what? Flip it and then double, right? Twice as long. So it'd be something like, I think it'll be somewhere around here. This is what -2u would look like. And then you do tip to tail on that and get your answer. Now, when you do it algebraically, right? When you do this algebraically, what you would do is first figure out what -2u is. Do you want to help me do that one real quick? What's -2u? Just take this. This is u, right? Multiply it by -2, and you get what? 2/8, right? And then in front of that, you're adding v, which is 2, 3. Is this okay that I'm just kind of leaving this to you? I don't want to be going too slow, but I don't want to go in too fast either. We're okay? You'll probably beg me to slow down later, just not yet. All right, so what's the difference between that and example 4? Now we're in R3, and notice I don't ask you to sketch it. It's because it'll be difficult to sketch. But all of these can be done mechanically. So how about we find, let's do C and D on example 4. We're going to find 4v minus 3u, and then we're going to find its magnitude, because we haven't found the magnitude of a vector yet, have we? No, we have not. So I'm going to write down, well, I guess I don't need to write them down if they're right here. Let's find 4v minus 3u. So this is 4 times the vector 2, 3, -5, minus 3 times u, which is -5, 7, -2. Everyone agree that that's 4v minus 3u? Now I'm going to do my scalar multiplication at this point. I'm going to pass the 4 through, pass the -3 through. Is that okay if I pass a -3? What do you think I'm going to have to replace the negative with if I pass the negative through? Plus sign. So this is going to become the vector 8, 12, what? -20? All right, that's 4v. And then plus the vector 15, -21, 6. Add together, we get the vector 23, -9, and -14. And now I grab my calculator, which I only have my phone today. So that's the answer to part C, right? That's the vector 4v minus 3u. Now I need its magnitude. So how do we find the magnitude of a three-dimensional vector? Well, the magnitude of this I'm just using the formula from the previous note, right? This one right here. The magnitude of a vector v in three-dimensional space is, how could we say this in math language? We would say this is the square root of the sum of the square of the components, right? It's the square root of the sum of the square of the components. So we square each component, we add them all together, and we take the square root. So this should be equal to the square root of, all right, well, you have your calculator. What's 23 squared plus negative 9 squared plus negative 14 squared? So what's 23 squared? I thought y'all were going to help me out. I guess I'm on my own up here. 529 plus 81 plus 196 root 806, which is approximately, that's the exact answer, right? Oh, that's approximately, so we use the wavy equal sign to let everyone know this is an approximation. 23.4, or 28.4, sorry. The vector would have a length of 28.4. Questions? We're okay? This is fun, huh? Okay, so I was going to show you something before I get on to that next one. Somehow this gets lost somewhere whenever we're going through these sections, but I want to practice two things. I'm going to give you a vector, and I'm going to ask you to give me what direction it's pointed in and how long it is. And then I'm going to do it the other way around. I'm going to give you a vector, I'm going to tell you how long it is and what direction it's pointed in. I want you to tell me what its components are. You need to be able to do both. Okay, so I'm going to do split screen here. Okay, you're given here the vector 2, negative 3. Find the length and the direction. So how would you like to do this? Do you want to draw it first? It's 2D, it's two-dimensional. This should be very easy to draw. Here's your vector. Should we call it something? V, U, W? You want to call it V? Okay, so there's our vector V, right? How long is it? So the length of V is the square root of 2 squared plus negative 3 squared. So 4 plus 9, right? Root 13. That's how long it is. So we've answered the first part. What direction is it pointed? So how are you going to do this? Well, inverse tangent. So this goes back to pre-cal. If you are looking at your standard two-dimensional sheet of paper and you pick a point out here and you call this point xy, and this is not on the unit circle, this is just a point sitting in space, then we can always measure the distance between that point and the origin. We could call that r. And we could also establish from that the angle that it makes with the positive x-axis, right? Then there is a relationship between the x, the y, the r, and the theta. And they are as follows. Anyone remember what they are? What is x, what is y, how is it connected to r and theta? X is r cosine theta. Do you believe that? Divide both sides by r. And don't you have cosine is x over r? Isn't that the relationship? Cosine of this triangle, right triangle, is x over r. And then similarly, you could establish that y is equal to r sine theta, right? That kind of ring a bell? So what we have out here, if we wanted to try and determine the angle of this vector, was that too much or y'all okay? Y'all need to respond. Y'all okay? Yes? Okay. Because usually, like when I go over here and I'm talking about this and everyone's still looking over here, I'm thinking that this was confusing, but no? Okay, so I'm trying to establish the angle, the direction. What am I referring to here when I say direction? The angle between the positive x-axis and the vector. It's this, not this inside, okay? That's called a reference angle from pre-cal, the shortest angle that goes to the x-axis. That's not what we want. The direction of this vector is the angle that goes all the way around. This formula works for all angles. So what we're going to do here is we're going to try and recover the angle. What was one more thing we had here? What was tangent theta on this picture? Y over x. And then if you take inverse tangent on both sides, you get theta is arctangent of y over x. So you can always recover the angle if you know the x and y coordinates of the point. We're going to kind of cheat, and that's what we're going to do over here. We're going to act like we have a point here, not a vector, a point. What would that point be in two-dimensional space? It'd be 2, -3 as a point, not a vector. And that's like the x and the y, and then we just plug in right here. Okay? So everyone go ahead and do that. Let's get your calculators out. And let's do the y coordinate, which was -3, divided by 2. Let me see what you get. What do you get? 56. So you're in degree mode or radian mode?
Degree.
Okay, so we'll do it in degrees. Is that all right with everyone?
Well, it was negative. I got -56.
So 3 negative divided by 2, arctangent, -56.31 degrees, approximately, right? Good enough? Is that an acceptable answer? Is that the direction of the vector?
Yes.
It actually is, because -56, if I say, hey, go -56 degrees, aren't you right there? That is equivalent to going around this direction. What you could not say is +56. +56 is that same length of angle or same measure of angle, but up. That's not the direction it's pointed. So you would have to go like that. Got it? Any questions? So
We're not completely barred from using the reference angle?
well, I guess yes you are, because, well, the reference angle here is not -56. The reference angle is, when you talk about reference angles, your reference angle is always between 0 and 90 degrees positive. Your reference angle is always a positive angle. So if you said -56, that's technically not a reference angle. Understand what I'm saying? Okay. I'll show you a slight variation of this where you could get yourself into trouble in just a second. Let's go the other way, though. Let me tell you that we're given some vector v, that its magnitude is √13, and that its angle, theta, with the x-axis is 56.31 degrees. It's the opposite information, right? So how are you going to go back? How are you going to go from this back to this vector, 2, -3? How do you do it? Oh, I forgot to put negative. Thank you. I forgot to put negative. I want it to be the same place. So how would we go backwards? Well, look, isn't the length of v, isn't that blue, the length of v equivalent to r from pre-cal? Isn't that the radius to this point? So this is actually r. And we also have theta. So if you just go to your two formulas, x was r cosine theta, and y was r sine theta, we should be able to get the x and y coordinates of the point. So this would be root 13 times cosine of negative 56.31 degrees. This one would be root 13 sine of negative 56.31 degrees. And you just get in your calculator and type those out. And you'll get something very close to 2 for the x and very, very close to negative 3. It's going to be off a little bit because we rounded right here. Make sense? You understand how to go both ways? Now R3 is more difficult. Why is R3 more difficult? What do you think? Let's say that, I don't know how easy this is going to be for you to see, but let's say that you know, like this is the origin. I'm in three-dimensional space. Say the x-axis is going out like that. The y-axis is going out this way, and then z is this way, right? And then I give you some vector. Okay, some vector. Its length should be easy, right? The length, we can get that with the square root formula. What about direction? See, in two-dimensional space, we all understood in two-dimensional space the direction was that angle, right? But in three-dimensional space, what am I talking about? The angle in reference to what? Like back to the x-axis? No matter which way I'm pointed, am I supposed to go back to the x-axis? Like, do you see that you have that third dimension? So we're going to have to table that for now. And you won't be asked to find an angle of a vector in three-dimensional space. All right? Not yet. We'll be able to get it, just not in this section. All right. What was I going to do? Oh, I was going to switch this up. I was going to make this, just real quick, what would happen if I make that negative? Then does the length change? No? Okay, this direction, these both are negative now, right? If you do that on your calculator, what do you get? Positive 56, right? Is that correct? So is theta positive 56.31 degrees? It's not. It's kind of correct. See, here's the problem. This has to do with the inverse trig function. Remember that whenever you had inverse trig functions, you had to restrict domains and all that stuff to make sure it had an inverse? See, we had negative over negative, didn't we? Which turns out to be positive. Your calculator doesn't know that, right? So your calculator is thinking that it was actually 2 positive 3. It thought that you were here, right? So it spit out the angle right here, which is 56.31 degrees. But that's not where your vector lives, does it? Where does your vector live? In the fourth quadrant, right? You're actually pointed, third quadrant. You're actually pointed down here, aren't you? So this answer is actually the reference angle. It's this angle right here. So what do you need to get your angle? Add 180 to it. So you have to be careful with these angles. Always make sure that maybe you draw a quick little sketch to make sure that your angle matches up with where it's supposed to be. This happens in pre-cal also. I know it's been a while since pre-cal, right? But this happens in pre-cal also. You have no way of knowing if these were both negative or both positive to start. I mean, we know, but your calculator doesn't. And does anyone remember the domain restriction for the inverse tan? Like it's only going to spit back, not the domain restriction. When you look at the arctangent function, the answers to this are always going to be between negative pi over 2 and pi over 2. So it's only going to ever spit out answers between here and here. It's never going to give you an angle over here. So if your vector's over there, you're going to have to realize that. We okay? All right. Moving along. Unit vectors. A unit vector is any vector with a length of 1. So as long as the vector has length 1, it's called a unit vector. And an example of this in two-dimensional space, if I take this blue vector, I can make it shorter, longer. No matter what, there's always a vector that's pointed in the same direction, right? That has a length of 1. No matter which way I point the blue one. I should always be able to find a unit vector in the same direction, even if I make blue shorter than length 1. There's still a vector that's pointed in the same direction that has a length of 1. The only exception to this would be if I put the 0 vector there, right? The 0 vector has no direction, so there's not a vector pointed in the same direction that has length 1. So everyone understand a unit vector is a vector with length 1. That's it. All right. The question is, if somebody gives you a vector, how can you find a vector that's pointed in the same direction as that vector but has a length of 1? So think about this vector. Let's say I give you this vector. Here it is. I call it u. There it is. All right? How long is u right now? You don't know, right? You don't know? So I could just call it the length of u. That's how long u is, right? So why don't I take the u vector, and why don't I multiply it, scalar multiplication, okay, by 1 over its own length? What would that do? That would scale it down, right? Remember, if you take a vector and multiply it by 1/2, it'll be half the length, right? If you take a vector and multiply it by 2, it'll double the length. Well, what if I take a vector u and I scale it down by its own length? Then how long should it be? 1 unit long. Yes? Yeah? So that's what this is saying. Someone gives you a vector in 2 or 3-dimensional space. We can always find a unit vector pointed in the same direction by computing the following. The vector divided by its own length, which is the same as 1 over the magnitude of the vector. That's not dot, that's just multiplication, scalar multiplication times u. All right, and that's it. That's all you have to do. It's a nice result. So find a unit vector which points in the same direction as v. You want to try that on your own real quick? Raise your hand when you have it. You don't have to get a decimal answer or anything. You just leave it in exact form. Anybody have it yet? No? Still working. Who's lost? It's okay to be lost. Anyone lost? You know what to do? What do you need to do? Find the length of v first, right? Just find its length. Okay, let's compute that first, which is square root of 2 squared plus 3 squared plus negative 5 squared. That's the square root of, what is it? 38. We're just going to leave it like that, okay? Square root of 38. That's how long that vector is. So what I need to do now is I need to take the original vector v, and I need to scale it down by that much. So 1 divided by that much is going to scale it down. So here's what I'm going to do. I'm going to take 1 over the magnitude of v times v itself. So do you see again, everyone needs to understand that the magnitude of v is a number. 1 over a number is a number. This is a scalar times a vector. This is scalar multiplication. So I'm scaling the vector by its own length. So I'm going to take 1 divided by root 38, and I'm going to multiply the vector 2, 3, negative 5 by that, right? Didn't we already say that if I take a vector and multiply it by any number other than 0, it will be parallel? It'll point in the same direction? Well, unless I multiply by negative, right? Then it flips it the opposite direction. So this is a positive number. So the answer to this should point in the same direction as my vector. It's just going to not be as long. And so just pass this through, and you get 2 over root 38, 3 over root 38, and negative 5 over root 38. If you take that vector, I promise you that it's pointed in the same direction as that one, and it has a unit length. How could you verify that it's a unit vector? How could you check it?
Find its length.
Find its length. You want to find the length of that? It's going to be super easy. Let's do it real quick. How long is this vector? Let's see. It's 1, yeah, but let's show it. Square root of first component squared. 4 over 38 plus second component squared. 9 over 38 plus 25 over 38. And your numerator is 38 when you put them all together. So that's 38 over 38. That's 1. Root 1 is 1. Check. Right? Now, what you could do, which is kind of a fun exercise, is show that this is true for an arbitrary vector. I'm not going to do it, okay? If you take that and divide it by its own length. So if I take this and divide each one of these by its own length, how long is this vector? That's how long it is, right? If I take that divided by this, that divided by this, that divided by this, that new vector, again, I guarantee has a unit length. How would you check? You take the square root. Trust me, just work it on your own. It's fun. Fun's relative, I guess. But you can verify that that's always going to work, no matter what your vector is. All right, so now we know if someone gives us a vector, we always know how to find one that's pointing in the same direction that has unit length. That will be useful to us later. Look, everything we're doing right now is for later, right? It's just a matter of, okay, when we get a bigger problem, we're going to look into our toolbox and we're going to be, there's that unit vector thing that we did, you know, and we got to know how to apply those formulas. All right, that leads us to what are called the standard basis vectors. So where are my linear algebra people? How many? No one's taken it yet? Anyone taken linear algebra? You took it. It's done. You're concurrently taking it, right? Okay. So let me just get through this, and I'll talk more about what I was going to say. Standard basis vectors in two-dimensional space. There are two important vectors in two-dimensional space we call the standard basis vectors in R2. They are I with this little up caret thing. We usually say I hat, like somebody's hat. I hat, it's the vector 1, 0. And then j hat, which is the vector 0, 1. And let me just draw them for you. I hat. Now that's 1 right there. And then j hat, that one. How many of you have seen or heard of I hat, j hat? Yeah, physics, right? All they are vectors, okay? They're just important. They're very special. Now let me show you why they're special with an animation. First of all, they are unit vectors. Do you agree that they're unit vectors? Can you just tell by looking they have length 1, each one? Okay. Also, every vector that you could ever think of in two-dimensional space can be written as some linear combination of those two vectors. So let me try and illustrate that with an example, or with this animation. Okay, so I have this vector up here, u, which is the vector 1, 1. I can always create the vector 1, 1 by somehow combining I hat and j hat together. In this case, is it obvious to you that if I add I hat and j hat together, right, I hat plus j hat, I would get 1, 1? Because what is I hat? 1, 0. And if I add that to 0, 1, I would get the vector 1, 1, right? But look at it visually. If I take this, tip to tail, take that one, slide it over, wouldn't I have u? Yes? Now I'm going to come in here, I'm going to pick some crazy arbitrary u. Ready? And there. Okay, there it is. So I picked some arbitrary u in two-dimensional space. Guaranteed, I should be able to create u by taking some combination of I and j. In this particular case, what I would do is I would take I would scale it by negative 2.038. What would that do? It would make it almost twice as long, right? And it would flip it over, okay, here. And then I'd take j and I'd multiply it by negative 1.15, which would flip it and make it a little bit longer. Then if I take these two red vectors and go tip to tail, I will be at this point. Y'all see that? Every vector in R2 can be rewritten as some combination of these two vectors. Linear combination meaning you scale them and add them. Understand? There's no way that anybody could come in here and pick a vector that I could not draw, that I could not write as a combination of I and j. So if I pick, let's say this vector right here, I'm going to call it w, all right? Then w automatically has two components to it, doesn't it? Yeah? Here's how I could always create the linear combination. What I would do is I would take 1, 0, I would add it to 0, 1, and what I would need is for the first component to turn out to be w1, right? So I would just scale this by w1 and scale this by w2. Do you agree that this would be this if I added them together? Yeah? This is what we mean by linear combination. Linear meaning we're adding, okay? Linear combination. Scaling this vector, put together creates this. But if I rewrite this in the I hat j hat notation, this is w1i plus w2j. Sorry, I hat j hat. This is a linear combination of those two standard basis vectors. Yeah? Are those the only two? I mean, okay, that's when we go to three-dimensional space, right? But let me kind of back this up again. Like this. This is going to be hard. Let me do it this way. Okay. Let's say we're now going to live in Robert's two-dimensional space, okay? I'm going to make up my own two-dimensional space right now. Ready? Here it is. It doesn't look like this. Okay? That's the one that you like, where everything's nice and perpendicular. Here's mine. What I'm going to do is I'm going to make up this vector. I'm going to call it R I hat. R for Robert. I hat because you kind of think of it the same way as I hat. Then I'm going to make another vector over here, and I'm going to call this one R j hat. Okay? What I'm claiming right now is that this to me in my system, that's my standard normal basis. Is there any way you could draw a vector that I couldn't get to with these two? So you tell me where to draw it. Where do you want me to go? Which way? Left, right? You want to go down, into the left, to the right? Which way? You want to go to the right, like this way? Okay, all that. That good enough? I can get to that, all right? How? How can I get to that?
Send our
Yeah, what I want you to do is imagine this. You see this parallel? This is running parallel. See that? These lines. See all these lines that are running parallel like this? Yes? And then with this vector, I'm going to run parallel lines like this. Good enough? You'll see it? So how could I get here? Let's see. What do I have to do to get here? If this is R1, Ri, sorry. What would I do? Try and get from here and then like this. Can I create this red vector? Can I create that red vector using this vector right here? Do y'all see this or not? Let me put something next to this so you can see it. The thing is, if I take a vector like this in standard two-dimensional space, it's easy to get to it. If you grid this out, running like this, it's easy to get here because you take I however many times, right? And then J however many times to get up. But you're basically moving along left and right in these increments, and you're moving up and down in increments. The same thing here. If I have these two standard vectors, as long as I stay within this grid, which is not squared up anymore, can I still get to this point? Yes. I mean, there's a way to do it. There's a certain multiple of this, right? I really want to try and show it. How about I do this? How about I take this red one and I point it in the other direction? Could I do that? And then eventually, if I make it long enough, wouldn't I be able to come back up with the blue vector to here? Yes? That's the way I would do it. That might be stretching it a little bit too far. But there is a point to me saying that, and this is for the linear algebra people. These two vectors in two-dimensional space are also called a basis for the space. They're a basis because you can draw any vector in that space with those two vectors. A standard basis, I hat, j hat, are so special because they have a couple of things going on. First, we said the length of them is what? 1. The length of them are 1. But they're also perpendicular to each other. And so in linear algebra, what they'll refer to this as is what's called an orthonormal basis. So I and J in linear algebra are referred to as an orthonormal basis. Ortho stands for the word orthogonal, which we're going to talk about today. Orthogonal means perpendicular. So you have two basis vectors that are perpendicular to each other. Normal means that they have unit length, and basis means they span the entire space. That's a very special basis, and that's why we like to use it, because it's an orthonormal basis. But this is an example of a basis, but it's not an orthonormal basis, because these don't have unit length, and they're not perpendicular to each other, but it still spans the space. Sorry, I'm off. I'm going to come back. Sorry, went off on a little tangent there. All right. Oops. Now in three-dimensional space, there's a little bit of a change. We just have a third component. So I hat is now, instead of 1, 0, it's 1, 0, 0. J hat is 0, 1, 0. And K hat is 0, 0, 1. And those vectors, 3D-wise, look like this. You have I comes down the x-axis, J goes down the y-axis, and K goes up like that. So this is I hat, J hat, K hat. And they all have unit length, right? Are they all perpendicular to each other? Yes, they are. And do you think you could draw a vector in here that I couldn't get to using those? It's impossible. Any vector you draw, I will be able to find it using some combination of these three vectors. So again, in three-dimensional space, this is an orthonormal basis. But for us, we just call them the standard basis vectors. All right, that's just some terminology. So this is a very, very simple example, all right? Let's not make it complicated. Write this V as a linear combination of standard basis vectors. Very simple to do. 2i plus 3j minus 5k. When I say I, j, k, please understand I mean I hat, j hat, k hat. That's it. We're done. Now, if someone gives you this, can you go back to that? Pretty simple, yeah? But just remember what it means. It means this. All right, that's what it means. It's three scalar multiplications of three different vectors, and then you combine them all together, and if you were to do that, you would get back this vector. But isn't this a lot easier to write than this? So I think that's why we prefer it in physics, shorter notation. But mathematicians, oh, we prefer that. That's even better. All right.
Will you always refer to it as standard basis vectors, or will you use like unit vector notation?
You mean if you're ever asked to convert like this?
Like
Yeah.
if you want a certain way, would you always just say standard basis vector notation?
I would specify use standard basis vectors if I wanted it. And I would never take off on a problem if you like this notation. If you prefer this, go ahead. But I'm going to use this as little as possible. I'm going to be up here using the angle brackets. When you do your homework, the problems they give you a mixture of both. All right? Is that it? Okay, 10-2 is over. And everyone knows where the homework for 10-2 is, right? Okay. All right, let's talk about now the dot product. All right, so there are, again, three different multiplications. There's an entire section here dedicated to one type of multiplication called the dot product. And here it is. Ugh. All right, so given two vectors in two-dimensional space, so if we have two-dimensional vectors, u and v, then u dot v is defined to be v1 u1 plus v2 u2. So all you're doing, I want you to see this, is you're multiplying the first components together, right? You're multiplying them together, and then you're adding to that the second two components together. So you're taking two numbers, multiplying them, two numbers, multiplying them, and then adding them. So the answer should be a what? A number, right? The dot product is the sum of the products of the components. It's vital to notice a dot product yields a number as the answer, not a new vector. This is strange because anytime we've had multiplication in the past, it's never behaved this way, right? If I take, again, the number 4 times 5, what was your answer? 20. A number, right? Two numbers, they put them together, you get a number. Great. Even if you take two functions and multiply them together, you always got a function, right? Now we're taking two vectors, we're multiplying them together, and we're getting a number, something that isn't even a vector anymore, right? That's the definition of a dot product. So we'll use this bolded dot to represent dot product instead of the regular multiplication dot. In three-dimensional space, it's the same story. You take the first components, multiply them, then add to that the second components, and then add to that the third components, multiplied together. Again, the answer is going to be a number. Weird, right? The natural question would be, what does that number represent, right? Like, we all know what 3 times 5 is, right? You can imagine that as being like 5 groups of 3. And so it makes sense that the answer would be 15, right? But what does a vector times dotted with a vector being a number, what does it represent? What does that numerical value mean? Yeah? Hopefully it means something, right? Not just some arbitrary number. Okay, but that's the mechanics of it. So a quick example. What's u dot v here? So I'll do this once, long notation. 2 times -3 plus -3 times 4 plus 5 times 7, right? That's what I'm doing? So -6 minus 12 plus 35, which is 17? You'll notice this when I'm doing if you watch me doing the homework videos, you'll see when I get to, my brain just completely just turns off. As soon as I see arithmetic, my brain's like, I guess it's kind of like, you know how computers like save memory for certain tasks, and like my brain just, as soon as it sees arithmetic, is like, do not commit effort to that, and shuts down. It's just arithmetic, yes?
So that number's scalar, what does it represent?
Yeah, I'm going to answer that. But I mean, it is important for us to wonder what it is, right? Let's just first make sure we can compute it. We can compute it? Yeah, we're happy? Okay, let's now figure out what the hell it means. So, well, before I get to that, some properties of the dot product. If you dot a vector with itself, u dot u, you get what? Its length squared. What? Okay, I take some vector u, which I'm calling u1, u2, right? If I dot it with itself, that means I'm going to take the vector u again, right? And let's dot it. So what's u dot u? By the definition, it's u1 times u1, right? Which is u1 squared, plus u2 times u2, which is u2 squared. Does that look familiar? Well, what's the magnitude of u? The square root of u1 squared plus u2 squared, isn't it? Isn't that the definition of the magnitude of u? Right? If I gave you this u and I said, hey, well, how big is that? How long is that? You would say that, right? But if I square this, right, isn't it this? See that? So that's where this is coming from. You take a vector, you dot it with itself. It gives you the length of the vector squared. That's only if you dot it with itself, though. Now, this property is the property that we use with standard multiplication of numbers. 3 times 4 is the same as 4 times 3, right? We call that the commutative law, not commutative. Commutative property, right, that you can flip multiplication around. You can do it with the dot product. It's going to turn out for the third multiplication, which is next class, the cross product. Cross product is not commutative. So we're going to learn that next class, that you can't flip cross products like that, but you can do it with a dot. That's good to know. Excuse me. Distributive property over addition. If you take two vectors and you add them together, what should you get? A vector, right? And then you take that new vector and you dot it with this vector. Whatever that answer is, it's the same as you dotting the u with the v, then adding the u dotted with the w. So it's almost like you're distributing the dot product over addition. That is a property of dot products. We could verify it, but we're just going to take it on faith.
If you add them first and get the result, can you just multiply them by the...
Dot it with that, yes. Uh-huh, yes. Wait, hold on. What are you saying?
Yeah, dotting it. Yeah, you add those together and then you...
Dot. You take that result and dot it. You can do it that way, or if you want, you can dot these. That'll give you a number. You dot those. That'll give you a number. You add them together, you get a number. Those two sides should be the same. If you scale a vector and then dot it with some other vector, you don't have to worry about the scalar. You can dot the two vectors first, then scale it. You can even move the scalar to the other vector. It all doesn't matter. So dot product is very well behaved. It lets you follow a lot of the rules that you had with standard numbers. Look at this one. The 0 vector dotted with v is 0. The number 0? The dot product of two vectors is always a number, isn't it? So is this correct notation? Yes, that is correct. This would be incorrect. That is not right, because that's not a number, right? So that is correct. Would this be correct? No, because you can't dot a scalar with a vector, right? That's a scalar, so that wouldn't make any sense. Your homework, they're going to ask you these things. They're going to give you like these different symbol representations. They're going to ask you, does this make any sense at all? Like, could you compute this? And you have to know when you can and can't. Y'all hanging in there?
Yes.
Thank you. I don't really feel like doing that. Unless we want to do it fast. Do we want to do it fast? Let's try and do this fast. All right. Can you tell me very quickly what 3u is? Okay, so it's -9, 12. Okay. And then I'm going to do what? Multiply, so dot product with VW. What's V plus W? 6, -3. Yes?
So the W is meant to be a vector then, right?
Yes, that's bad notation here. Hold on, let me correct it in my notes. Thank you for pointing that out. All right, so then dot these. What do you get when you dot these? So -9 times 6, -54, and then plus, and then 12 times -3, which is -36, and you get -90. Okay, -90. Okay? Now you could have used properties on this. You could have, if you wanted to, you could have done 3u dot v plus 3u dot w. And if you would have done that, you would have also got -90. But I just did it, I guess, the way that most people would have. Take care of this, put them together. All right, we still want to know what the hell this dot product means, right? So we have this extremely important theorem. It's called the dot product theorem. Now, I'm not proving this theorem. I believe the book does. I could be mistaken. Hey, I forgot last time to pass around the sign-in sheet because I do take attendance. So please find your name. If your name's not on this list, write your name on the bottom. And then just initial in the date. And if you were here last time, just initial. If you weren't here last time, I guess you could act like you were. It doesn't matter. But just do today and last class, please. So 2 initials. And when this goes around, make sure you move it around the room, okay? Don't just let it sit on your table. So I'm not going to prove this theorem. Let me see if they prove it in the book. Yes, the proof is in the book. So since it is in the book, I won't commit time to it. It's kind of cool. They use some law of cosines and things like that. It's on page 552. Some proofs in this calculus book just can't be done because the proofs are too advanced. When the proofs are easy enough for a student at this level to follow, they'll put the proof right there in the section, which in this case they did. So I would encourage you to go and take a look at it. I'm not going to commit time to the proof. But we are definitely going to put a huge asterisk next to this and say, guess what? we are going to put this into our memory banks. So you may be like me and not be able to do negative 16 minus 54 plus 13 because your brain just says, who cares? This one you need to put in there, okay? So reserve space for that. U dot V is equal to the magnitude of U times the magnitude of V times cosine theta. Now these are just regular scalar multiplications in there, okay? They're not dots. Is that a question?
So whenever you're writing in 3 dimensions, does it remain cosine theta and
Yes.
having another
It's,
magnitude?
nope. These vectors, right now I'm not telling you where these vectors live, right? So these could be 3-dimensional vectors. This is what's amazing about this theorem. It doesn't matter where your vectors are. 2D, 3D, 4D, doesn't matter where they are, okay? If you take two vectors, all right, here they are. 2 vectors, different lengths, just for fun. Okay, if I take a vector U, I take a vector V, sitting there in 3-dimensional space, and I dot them, what happens is I take the length of this one and the length of this one and multiply that answer together, and then I take cosine of the angle between them. So what do I mean by cosine of the angle between them? Well, they're 3-dimensional, right? So I can move them along without, as long as I don't change the direction, right? So I'm going to just move this one to match up right there. Do you see that? Now if we look at this in a plane, like this flat sheet, I'm pointing it at you because you're asking, right? Everyone's, see that plane that I've made right there? If we turn that plane flat, this is the angle we're talking about, all right? So if I take any 2 vectors, no matter what space they're in, and I attach tail to tail, right? And then look at that flat sheet of paper that they both go through, like that, that's the angle, theta. Understand that? So this theorem connects the dot product to the length of the vectors and the angle between them. Now let's look at some results of this. There are some big time results of that theorem. First of all, if we're given 2 vectors, the angle between them must be between 0 and pi. I broke my vectors. I should have kept them here. If I take 2 vectors, it doesn't matter if we're on a flat sheet of paper or in 3-dimensional space, the angle between them must be between 0 and pi. So let's imagine this. I take these 2 vectors. That one's pointed over here. This one's pointed over here, right? If I take them and go tail to tail, right, the angle between them is between 0 and pi, isn't it? Yes? So when we say the angle between them, there's going to be a smallest angle. Because you could go this angle back this way, right? That would be bigger than pi. But the shortest, the smallest angle is this one. So what about if they're pointed exactly in opposite directions? The angle between them is pi, isn't it? And it's okay to be pi. That's why it's less than or equal to. So it's either this, or you could also have what? Parallel vectors that are pointed in the same direction, like this. What's the angle between those? 0. So no matter what, if someone gives me 2 vectors, the angle between them must always be between 0 and 180, yeah? Okay, now let's consider the cosine function from pre-cal. So what I'm doing is I'm about to look at this in more detail. U dot V equals magnitude of U, magnitude of V, cosine theta. Think about cosine theta from pre-cal. If theta is 0, cosine is 1? Yeah? So if the angle between the 2 vectors is 0, then what does the dot product represent? If the angle between 2 vectors is 0, what does the dot product represent?
Negative.
This is a 1 now, isn't it? So it's just what? The dot product is just their lengths multiplied. That's all it is. Understand? So if your angles are pointed in the same direction, then the dot product represents the product of their lengths. It's a number. It's the length of each one multiplied together. Now let's look at another important angle. What if the angle between the 2 vectors is pi over 2? That means that they're perpendicular, right? And what happens to cosine at pi over 2? Cosine of pi over 2 is 0. And therefore, the lengths don't matter, right? The dot product is 0. And this is probably the biggest result we're going to have. I think I'm going to put it on the board here in a second. But what if you have two vectors and you're trying to figure out if they are perpendicular or not? Well, what do you think? If I give you two vectors, say, are they perpendicular? How do you think you'll be able to check?
Take the dot product.
Take the dot product. What does it need to be? 0. That's it. That's the check to see if two vectors are perpendicular. It's beautiful. It's simple arithmetic. If you want to know if two vectors are perpendicular or not, all you have to do is take their dot product. If the dot product is 0, they are perpendicular. Now, another word for perpendicular, I don't have it here. I have it in a second. Never mind. Okay, so let's move on. Oh yeah, there it is. Right here. This is a big part of the notes. That's why I've highlighted it here. Two vectors u and v are said to be orthogonal, which means perpendicular. All right? If and only if u dot v is 0. Now, what does if and only if mean?
It's equivalence.
Yeah, I've talked about this with different students who have had me in the past, but I know there are some people who are wanting to be math majors and stuff. Anytime you see if and only if, it's an important thing. It means a double implication. It means that it goes both directions. I'll give you an example. If you're from San Antonio, then you're from Texas. Is that true? If you're from, let's just say you're legally in San Antonio, right? You're registered, whatever. Let's not get into these different arguments. Okay, you live in San Antonio, you live in Texas, yes? So we could say this, San Antonio resident implies Texas resident, yes? Does it work the other way around? If you're from Texas, does that mean you have to be from San Antonio? No. So this would not be a double implication. It doesn't work both directions. If it does go both directions, it's called an if and only if statement. It's a double implication, and usually we put a double arrow but going in both directions between the two statements. Okay? That's what this is. This is saying if somebody gives me two vectors, right? Where are they? If somebody gives me two vectors that are orthogonal, guess what? The dot product must be 0. And if somebody gives me two vectors and their dot product is 0, then they must be orthogonal. They must be perpendicular. So both directions. Do you understand the subtle difference in there? And that is a huge deal, because this is going to be our standard way of checking, like I just said, whether or not two vectors are perpendicular. Orthogonal. Now, go back to the formula that I erased here a second ago. Going back to that good old dot product. Does everyone agree that the magnitude of u is a positive number? The length of a vector is positive? Should be, right? The length of this vector should be positive? Yes? So the only thing that could possibly make the dot product become a negative number is the value of cosine, isn't it? And that's what the next note says. Here it is. When your theta, when the angle between your two vectors is between 0 and pi over 2. So if your angle is something like in here, what is cosine of an angle that's between 0 and pi over 2? Is it positive or negative? Positive, right? So if the angle between your two vectors is between 0 and pi over 2, then this will be a positive number, and the dot product therefore is positive. Now, if your angle between your two vectors happens to be bigger than pi over 2, right? Then what's going to happen? Cosine of that would be what? Negative. So your dot product would be negative. And I have an illustration of that on the next animation. Right here. So does everyone see these two vectors? Okay. What I'm having the computer do is do their dot product. Right now, do you see that the dot product is -2? The computer's doing that in the background, yes? Well, what is it being negative tell us? That the angle between them is obtuse, bigger than pi over 2. Automatically, we know that. But if I take this vector and I move it over here, oops, then look at the value of the dot product. What's happening to it as I move it over? Still negative, right? What's it getting closer to? 0, huh? I wonder why. Because when I get perpendicular, what's going to happen? It is 0, right? And then as soon as I get smaller than pi over 2, it's now a positive dot product, right? And that's because I have an acute angle between the two. Do y'all see the connection? Y'all see that? Okay. If I point this in the same direction, what's going to happen if I make this on that circle and I bring it down right on top of the other one? What should the dot product equal? Should be 1, right? Because it should be the product of their two lengths, shouldn't it? And 1 times 1 should be 1. What if I take that and I drag it out to 2? Should be 1 times 2, which is 2. Pretty close, 1.99. Take it out to 3. The dot product is the length of this one times the length of this one. What happens if I take this one and I drag it all the way around to the other side to negative 3? What do you think it's going to be? It's the product of the two lengths again. 1 times this length 3, but because it's an obtuse angle, it's negative. Make sense? Now, you could take this out and do it in 3-dimensional space, but it's so much easier to illustrate it in 2-dimensional space. Man, where's the time go in this class? This one's almost a trivial example. What's the dot product if I give you the lengths of the two vectors and the angle between them? Is this even worth doing? U dot V is magnitude of U, magnitude of V, cosine of the angle between them. What's the magnitude of U? 3, magnitude of V, 7, cosine of 31 degrees. Get your calculator out. Make sure you're in degree mode. What do you get? About 18? Is that what you said? Okay. Well, that's good because it being a positive answer, you know, the angle was acute, so that kind of makes me feel better that that's right. Are these two vectors orthogonal or not? No? Why not? Okay, so all we have to do is check the dot product, right? Take the dot product, see if it's 0. So what is, do I have to do U dot V or can I do V dot U? It doesn't matter which one I do, right? Because it's commutative? Okay, so dot it, let's see. 2 times 6, right? That's what we're doing. Plus 4 times negative 3, which is 0. Are they orthogonal? Yes. Right? Isn't that a nice check? I mean, come on, that beats what you might have wanted to do, which was draw the first one and then draw the other one and go, yeah, I think that's orthogonal. Or try and do some sort of Pythagorean right triangle, hope for the best thing. That's not fun, right? You would have to like check the length of this and then the length of that, and then you would try and get the length of this, and then you'd try and confirm. Part of your homework was that. You don't need it anymore. It's easier now to check if a triangle is right by just looking at the vectors. How many of you did the homework where you had to see if the triangle was a right triangle or not? Anyone do that? So they gave you like 3 points in space, right? And then something like that, and you were saying, is that a right triangle? So what you did is you found the length of each of these sides, right? Okay, no longer necessary. If I want to know if that's a right angle, all I do is I come up with this vector, I call it U. I come up with this vector, I call it V. I dot them. If it's 0, it's a right angle. I don't need to check lengths. Much easier this way. Now, let's say that you dotted those and it was 0. You'd be right triangle done. What if it wasn't 0? Well, then you would just do this vector and dot those. If it was 0, it's a right triangle. If it's not, then move on. You have to do this one and this one. But the dot product is much easier to do than all that other stuff. All right, so here's something a little more abstract. You're given two vectors. U is the vector 2, negative 2, 6. The vector V is A, 3A, negative 2A. And just for fun, let's just make this one A squared. And find the A such that these are orthogonal vectors. I don't even know if there's going to be an answer. Okay? Because I just tweaked the problem. It may not be possible. So what do we need? We need, right, that U dot V be equal to 0, right? That's what we need for these to be orthogonal. So what is U dot V? Well, 2 times A, right? So 2A plus what? Negative 6A squared or minus 6A squared. I'll put it like this. And then the last thing, minus 12A. Is that equal to 0? When is that equal to 0? That's what I need, right? Shit. Let's see. I don't know if we're going to be able to get this. This is negative 6A squared minus 10A equals 0, right? Combining like terms. And this is a quadratic. It factors pretty easily, doesn't it? A is factored out, or how about, what do you want to factor out? A, negative 2A, and be left with 3A plus 5 equals 0. Agree with that? Can you give me the two solutions? A is 0, and then A is negative 5/3. All right, so let's look at A is 0 first. If A is 0, then V is a 0 vector, right? And if you dot the 0 vector with anything, you're going to get 0, right? That's weird. Think about that. The 0 vector dotted with any vector should be what? 0. That means that the 0 vector is orthogonal to every vector, right? That's weird, though. So when we talk about orthogonality, we always say two non-zero vectors are orthogonal if and only if dot product is 0. So we always want to be playing with vectors that are not the 0 vector. So this should happen. The fact that this happens isn't a surprise. If we just make this the 0 vector, we're always going to get dot product of 0. But there's another solution that's not trivial, and that's this one. So I'm claiming that if A is negative 5/3, that should work. So let's go back and rewrite that vector, V. Negative 5/3. And what? We have to do 3 times negative 5/3 squared. So what's negative 5/3 squared? 25/9 times 3. 75/9. Which is, well, I'll just leave it 75/9. Who cares? We could reduce that, right? And then negative 2 times this, which is 10/3. Y'all with me? All right. What we are hoping for is that if I dot this with U, I should get 0, right? Where? The 3 is on the top, though. The 3 is like a 3 over 1. So the 3 goes across the top to the 25.
Right, 75. But then when you square the 3,
Hold on. So you square this first. 25 ninths. 3 times that, 3 goes across the top, 75 over 9. 3 over 1. So that's right. Is that what you're referring to? Okay. We all good with this? Anybody check it? We're out of time. Anyone check it with you? What happens if you dot this with you? Can we dot it real quick? What's 2 times that? Negative 10 thirds plus, what's negative 2 times that? It's negative 150 over 9, and then what's 6 times this? 60 thirds. Get a common denominator? Or just reduce that. I guess we never reduced it, so what is this reduced? 50 thirds? There we go, we're done. That's 0, isn't it? Right? This is negative 60 thirds plus 60 thirds, that's 0. All right, so at least get through your 10.2 homework. We're into 10.3. See how much further we have. Yeah, we still got some more important stuff in 10.3. But we'll finish 10.3 next time for sure, and then we'll get into cross product. That sign-in sheet get around to everyone? Okay. All right, everyone. Have a great rest of your day. See you Wednesday. And try and get to the. Here, hold on, let me get this.